It's a true pleasure to be here and honor also the conference where we celebrate Damian. I'll be talking about a joint project with Miklos and Damian. It's actually a project that they started together, and then they were kind enough to let me in. This is meant to be a gentle introduction to the two concepts that appear in the title of the talk. So I put some boxes here, and each box is supposed to represent a category. I already put CW complexes on the side of algebraic topology here, and I put groupoids on the side of group theory. And the dialogue between these two categories is foremost established through the fundamental groupoid functor. This P denotes the fundamental groupoid functor, which takes CW complex to its fundamental groupoid. Now, by the fundamental groupoid of a CW complex, I mean the groupoid where the objects are the zero cells, the vertices of the groupoid, and the morphisms are homotopy classes of paths relative to endpoints. So I have some slides, but I promise I'll use them responsibly. So I wrote the definition of a groupoid just to give you a signal that I will try to explain everything slowly and carefully. That's the idea of the talk. Oh, sorry. So I already told you what I want to put here. This will be the category of discrete standard Borel groupoids, which I will abbreviate as SBGs. But first, a word about groupoids. So I usually use this letter as a name of a groupoid, and I think of a groupoid algebraically as a set of partially composable arrows, and I denote by G0 the set of identity morphisms from which we can recuperate the objects, right? So here is, So here's the definition of a discrete standard Borel groupoid. The short definition is that a discrete standard Borel groupoid, G, is an internal groupoid in the category of standard Borel spaces and Borel maps with countable fibers. The longer definition is that G is a groupoid, but it's also a standard Borel space. G0 is a Borel subset of G, and all structure maps, domain, codomain, composition, inversion, are countable to one Borel maps. Okay. So now the idea is to find something to put here. And I want to present you with a proposal of something sensible to put on this side. By the way, I chose here CW complexes as the right category for topological spaces because I'm thinking of applying the methods of algebraic topology to group theory. And there seems to be a consensus that for that, the right type of spaces to work with are CW complexes. Okay, so on this side, I will put SBCW complexes. Standard Borel CW complexes. Before I show you what they are, I want to fix some notation about CW complexes. Now, let K be a CW complex. I will use this symbol to denote the set of d-dimensional cells of K. Okay? K brackets D is the set of d-dimensional cells of K. Now, by a CW morphism, I mean a continuous map between CW complexes that maps open cells homeomorphically onto open cells necessarily of the same dimension. So this is a very combinatorial type of map. Maybe I write here. So if phi is a CW morphism, it maps open cells homeomorphically onto open cells. So it maps closed cells onto closed cells. And the combinatorial aspect of phi can be captured by a sequence of functions which tell you how phi maps the d-dimensional cells of K onto d-dimensional cells of L. If this is not clear enough, then I'll give you the definition. Right? You take a D cell here, and then you apply phi, that's a D cell in L. Okay? Now, let me give you, I think I move here. Now let me give you one example of a standard Borel CW complex. This example is simple, but it's fundamental because it enters into the definition of, into the general definition of standard Borel CW complex. And so the idea is you take a standard Borel space. And you take a finite CW complex. Now, I will put another structure on U. Now, consider U as a zero-dimensional CW complex. And consider, and for each D greater or equal than 0, consider a CD. Again, this is the set of d-dimensional cells of C as a discrete standard Borel space. Okay, so C is finite. So in dimension D, you have finitely many cells. So every subset is Borel. Now I have, now I will define something that I will call a char domain. And that will be the product of U and C. Now think about this product. We put a CW structure on U. It's just a discrete topology, right? It's a zero-dimensional space. So we can take the product CW structure. Okay. So I have a CW structure here, but also for every D, let's look at the set of d-dimensional cells. And you know how this works. Here, all cells are zero-dimensional. So what are my d-dimensional cells in this product? I can identify them with U times d-dimensional cells in C. Okay? And now I have a standard Borel space structure here, standard Borel space structure here. I can take the product standard Borel space structure. Okay? So this is one example of a standard Borel CW complex. We have, so what do we have? We have CW complex, And in each dimension, we have a standard Borel space structure on the set of cells of that dimension. So let me give you an example. So you take U to be anything, and you take C to be something simple. So I will take C to be an interval, 2 0 cells, one cell, and might be a good idea to give them names, V1, V2, E. Okay, so now let's look at the product. What can I say about the product? Well, you see, you have 2 copies of U. These are not categories, they're just copies of U. Okay, the first copy corresponds to V1. Remember, you multiply U with V1 and you get a bunch of 0 cells. That's the first copy. The second copy corresponds to V2. Okay, and now I take a point here, X, and I have a corresponding, I take a point X and I have a corresponding point X on the other side. And then I have an edge connecting them, right? I take another point, epsilon, there's a epsilon here, and there is an edge. There is another point, corresponding point here, there is an edge. Okay? So I hope this is clear enough. So it's this kind of picture that you should have in mind. And now remember, I call this a chart domain. Of course, I will have charts. And this is the definition of a chart. So let U times C be a chart domain, something like this. And let K be a CW complex whose set of D cells for every D is equipped with a standard Borel space structure. Okay. Something like what we had here. A chart domain is a CW morphism where this is our domain, and here we have some space CW complex K. And so we have phi, which is a CW morphism. And again, mind you that a CW morphism is a very nice type of map between CW complexes. It takes open cells homeomorphically onto open cells. And then you see the first condition. It's really a simple condition. If you look at the product of X and C, X is any point in U. You can consider this product as a subcomplex of the chart domain. Here's an example. So if we have X here, so the product is this subcomplex. Okay, and then the first condition says that phi takes this guy injectively into K. Okay, but you see what that means is that CW morphism is a bit of general topology. CW morphisms, the image of a CW morphism is always a subcomplex of the codomain. Okay, and if it's injective, then it's an embedding. And it's not only embedding, but it's an embedding that preserves the CW structure. So what that means is that here in K, you will see something that looks exactly the same. Okay, you will see a copy of C inside of K. So that's the first condition. The second condition, sorry, this is not. Don't bother too hard to read this. I will explain it more carefully. So the idea is that you take a cell in any dimension, okay, and then you see you can look at this subset, okay, and you can identify this with U. Okay, this is not the same. This is a D-dimensional cell, right? And then remember the map phi d will take this to k d. So, so now what do we have? So this is a cell. This is a set of d-dimensional cells, which will get mapped to. So every cell here will be mapped to some d-dimensional cell in K. But here I have a standard Borel space structure, and here I have a standard Borel space structure, and then the condition says that this map should be a Borel injection. Okay. So if we go back to this picture, my cell E can be the vertex V1. Yeah.
What is a Borel injection? Injection?
And it's a no, it's no, there's no measure. Yes, it's a Borel map which is injective. Yeah. Yeah. So E can be this one vertex, and then what is this? What is this set? Well, it's just this copy of U, and then we are saying that this phi will map this copy of U injectively into 0 cells in K by a Borel map, right? And the same holds for this copy here, okay? And the same holds for the 1 cells here. So if I take another 1 cell, you see it cannot go to the same 1 cell here, so it has to go somewhere else. Okay, but let's see, where else can it go? Can it go here? Right, it cannot go here because you see you have then you are mapping 2 different vertices to the same vertex here, so that's not allowed. But look, it's allowed to do something like this. Okay, because it's allowed to map something from here to the same place as you map something from here. Okay. Okay, so let me now give you the general. I won't give you the general definition. Now I will tell you what is one-dimensional standard Borel CW complex. Of course, I should begin with a zero-dimensional standard Borel CW complex, but a zero-dimensional standard Borel CW complex is just a zero-dimensional CW complex equipped with a structure of a standard Borel space. Okay, so let's go to dimension 1 now. One-dimensional standard Borel CW complex is a one-dimensional CW complex, okay, that satisfies 2 conditions. The first condition says that the set of 0 cells and the set of 1 cells are both equipped with a standard Borel space structure. The second condition, it's a bit more technical, so let me just write quickly the important information here. It says that, you see, the set of 1 cells admits a countable Borel partition. So the 1 cells are divided into countably many Borel parts. I like to refer to the Borel parts as bundles of cells. And then for each J, we have a finite CW complex Cj and a chart. Okay, and there is one more condition which I will write and then explain. Okay, so so you have countably many bundles of cells. for each bundle of cells, you have a space, Cj, a CW complex. This CW complex is either an interval or is a circle. Why these two possibilities? Because if you look at one cell in a CW complex, it's either attached to two different cells and then it's an interval, or it's attached to a single cell and then you have a circle. Okay? So this Cj tells you what is the structure of all cells in this bundle. They all look like Cj. That's the first. That's one of the consequences of phi being a chart. Now, what does this condition say? It looks silly, but you see, if Cj is an interval, then we are here at this example. And then I want to think of U, which now will be Uj, as a set of names for the one cells. Okay? And so it's a set of names which comes with a standard Borel space structure. And so instead of writing X here, we will have a name of a cell. Okay? And what this tells you is that the cell corresponding attached to the name tau will be actually mapped to the cell tau. Okay? That's the condition. And so if you think about it, it's a very simple idea. So you see in the chart domain, you have the one cells put one next to the other in a very free way. Okay? And then the chart tells you how these one cells are distributed around the complex K. But they have to be, you see it's a chart, so you have a nice structure here. They must be distributed in a nice way. That's the idea. Any questions? Yeah.
Can I ask an offensive question?
Mm-hmm.
So why is it a good definition? Why in one-dimensional case, if you're just asking the endpoint map in another pairs to be Borel, why is it not sufficient?
Just instead of looking at the circle, is that the question? Or?
No, you have the set, you have a map from the set of one cells, the set of subsets of one or two points,
Mm-hmm.
and just writing that this map is Borel.
Because I want to generalize. So you want to kind of go to a simplicial data. Yes. Yes, I am.
No, that's Borel structure. No, fiber.
Which one for K1? Yeah. Yeah, I understand. You right. You want to do, but then you're thinking of a simplicial structure, right? So that would be a more reasonable definition. And yeah, I mean, this is a silly definition for a one-dimensional CW complex. It can be put in much better terms, but I want to generalize, and this is the right way to do it. So here is the two-dimensional version. So now it's the same thing, the same first condition. Now you have 0, 1, and two-dimensional cells. For every D, the D-dimensional cells should come with a structure of a standard Borel space. The second condition is, of course, that the one skeleton of K should be a one-dimensional standard Borel CW complex. Okay. And here's the third condition, and something is off here. Sorry, that should not be there. So here is the third condition, and the third condition is really the two-dimensional analog of this condition. You see now the difference is that Cj, so again you have a bundle of cells. You have a bundle of cells, but now Cj represents the carriers of these cells, and they all have the same carriers. Okay, the carrier of a cell is the smallest subcomplex that contains the cell. So you see, we don't want to restrict the type of CW complexes that we consider. So I can have something like this. This is perfectly fine. A cell attached in that way. And this will be its carrier. This edge is part of what carries this cell. So you might have things like this. And then everything else is the same, like in the one-dimensional case. Okay? So the chart tells you how these carriers fit inside of the space. They should be nicely distributed inside. And there is, of course, one more condition, which I won't state. It's a technical condition, which tells you that the charts for the one cells and the charts for the two cells should be compatible. Some diagram should commute, right? And this is just to guarantee that whenever you try to do something sensible here, everything you do will be measurable. Okay? So that's the definition of a two-dimensional CW complex. I want to show you the general definition, but it follows this pattern, right? Okay, now now we come back here. A theorem, there is a fundamental groupoid functor. It's the same fundamental group. Is the same functor, right? The zero cells are the objects. The morphisms are homotopy classes of paths relative to endpoints. But because now we have some standard Borel structure here, the groupoid gets a natural structure of a standard Borel groupoid. Okay. And I have two more boxes, and these are reserved for the measure version. So measure preserving SBGs and measure preserving standard Borel CW complexes. So let me tell you what they are. A measure preserving standard Borel groupoid is a pair groupoid measure consisting of a standard Borel groupoid, Borel measure, but the measure is on the set of units, and the measure is required to be preserved by the arrows of the groupoid. Okay.
So in this functor phi, what will be the unit space of the resulting groupoid? Like what?
It will be the zero cells.
The zero cells?
Mm-hmm.
Okay.
Here also.
Yeah.
So, right, everybody knows what this means, but let me say it anyway. So, on the set of units, I have a measure, right, to be preserved by the arrow. So the groupoid means that if you take a Borel subset A, Borel subset B, and you take a Borel injection F that moves points along the arrows of the groupoid, then the measure of A should be equal to the measure of B. That's standard definition. And then, of course, I have a similar definition for, on this side, a measure preserving standard Borel CW complex is a standard Borel CW complex together with a measure, Borel measure, on the set of zero-dimensional cells. And this measure should be preserved by the edges. So if you move, so it's the same condition. That's what we have here. Now this represent the edges of the complex. Okay, but you see, if you have, so what I have is I have a measure on zero cells. Okay. Now this measure on zero cells will induce a measure on D cells for every D. Let me explain how that works. Remember that we have charts. When you put the charts together, we call that an atlas, right? And so we have a countable partition here. Okay, and we have a chart Okay. Now, if I take any vertex of this complex, V, right, I can consider again this product. This can be identified, and here I have something like this, goes to 0 cells. But remember, it's part of the definition of a chart that this should be a Borel injection. Okay? So I can look at the image, it's a Borel subset here. I can restrict the measure to that Borel subset, and I can pull it to uj. So I have a measure here. And I have a measure for every uj, so I take the disjoint union, and that gives me a measure on the space of these cells. Okay. Okay. So again, there is a functor here. It's the same functor, fundamental groupoid functor. Everything works nicely because you have a measure here that will give you a measure on the standard Borel groupoid. Okay, so now I want to pursue this analogy. So the idea is that you want to develop a dialogue here that similar to this dialogue here. Okay, so remember that groups have classifying spaces. A classifying space for a group gamma is a connected CW complex K whose fundamental group is equal to gamma or is isomorphic to gamma, and all higher homotopic groups vanish. Equivalent way of saying this condition, all higher homotopic groups vanish, is that the universal cover of the space is contractible. Well, these guys also have classifying spaces. Okay. The way you can define them is that the classifying space for, let's say, a measure-preserving standard Borel groupoid is a measure-preserving standard Borel CW complex K, where the fundamental groupoid is G, E, and all higher dimensional homotopy groups vanish. Well, you know, here we don't have connectivity, right? Because a standard Borel CW complex, I mean, it doesn't have to be very large, but that's what you should be thinking about. So you imagine that in every dimension where you have cells, you have uncountably many cells, okay? But if you look at the connected components, on each connected component, you have countably many cells, okay? So you will have uncountably many connected components. And so what this vanishing of higher homotopy groups is saying is that all higher homotopy groups vanish on almost all connected components. Okay? Now, I gave you the objects, but these are categories. They are also maps, they are morphisms. I won't tell you what they are, they're more technical definitions. But there is an appropriate notion of a morphism here and here. And there is an appropriate notion of homotopy, so there is an appropriate notion of homotopy equivalence. And just like in the case of groups, classifying spaces are unique up to homotopy equivalence. Yeah?
Can I ask you one question about morphism? Because what we define as CW morphism is actually much more restrictive than what you would call a morphism in the category of CW morphism.
Because you're catching me on... Oh, no, I won't consider that kind of morphisms here. I will, for example, I just needed that for the definition of charts. Yes, sorry, that's not the morphism that I want to consider. Yeah, maybe it was a bad choice to use morphism. Because I want to take the objects to be the 0 cells, then I would take here cellular maps. Yeah. Okay, so again, the idea is that the classifying space is unique up to homotopy equivalence. So what that tells you is that any type of algebraic topology that you want to do on the classifying space, any type of reasonable invariant that you would like to define, can be considered as an invariant of the standard Borel groupoid. Okay. Okay. So, but now I want to go in another direction, more combinatorial. Recall that a group gamma is said to be of type Fn if there exists a classifying space for gamma having finite n skeleton. Okay. A group has type F1 if and only if it is finitely generated. And it has type F2 if and only if it is finitely presented. And it has type F3, and I don't know what to say, that there is no algebraic condition that I can easily say. Well, the same definition. Measure preserving standard Borel groupoid gamma is of type Fn if there exists a classifying space K for G with right, appropriate notion of a finite n skeleton. Right? You should have a finite measure of cells in each dimension up to n. Okay. Now here's another concept from this dialogue. The n-dimensional truncated Euler characteristic of a group gamma of type Fn is defined as this infimum, which I guess I can write here. Where did I put the eraser? The femum of okay, you get it. First of all, why do I have this -1 to the n? Well, a word about my notation. These are parentheses. So this means the n skeleton of K. Okay, this is the n skeleton of K. K is a classifying space for gamma, having finite n skeleton. I take the n skeleton. It's finite, so it has an Euler characteristic, which is well defined. And I put this -1 to the n because I want the top cells, the n-dimensional cells, to be counted with a positive sign. That's the idea. So you start with positive sign at the n cells, and then you alternate the sign. Okay. I have a corresponding notion for NP standard Borel groupoids. It's the same definition. It looks exactly the same. The difference is that we have G here. But what is this guy? Well, you can guess what it is. You don't actually want to take the, you want to take something like a measure Euler characteristic. So go from 0 to, yes, n. And remember, this is my measure on the I cells. And this is the set of I cells. So here I put the measure of I cells. I alternate. Okay. So this first definition, the n-dimensional truncated Euler characteristic here, enters into the definition of rank gradient. How much time do I have? 15? So rank gradient was mentioned today. Here's the definition. These are the higher dimensional versions. So you have gamma, a group of type Fn. You take a filtration by finding the subgroups. And then you define, then all this, you see gamma is of type Fn, so all these subgroups are for type Fn. And then you define the n-dimensional rank gradient to be this limit. The limit exists because this is a decreasing sequence. Okay. It tell you another way to think about this. You see, I didn't say this, but I am, of course, thinking about countable groups. Okay. Now, if I take a countable group, I can think of it as a groupoid with one object and one morphism for each element of the group. Okay. And then I can put measure here, measure 1. Okay. And now I have a standard Borel groupoid. So kind of this category gets inside of this one. But now you see I have definition of Fn for standard Borel groupoids, and I have definition of Fn for groups. I have also this notion of a truncated Euler characteristic. Well, fortunately, when you think of a group in this way, all these notions coincide. Okay, they're the same thing. Another thing I want to say here is that this quantity can be described in the following way. You see the group gamma acts on this coset space. And on this coset space, I can put a uniform probability measure, and then gamma acts in a probability measure preserving way. Okay? And then I can associate to this action, let's call it alpha, a groupoid, the action groupoid. You know how it works. You look at the space, you have a point x, you look at an element, that element moves that point to some other point. Well, your space is the set of objects, and for each x, maybe it's better to call it gamma x, for each x object and gamma element of the group, you have a morphism gamma x. Okay? Then this quantity here, in the definition of rank gradient, is exactly the truncated Euler characteristic of this action groupoid. Okay. Now I tell you the definition of an n-cost. Well, it sort of pushes this idea further. Right? Instead of looking at these actions only, I will look at all possible actions. So let gamma be a countable group. The n-cost of gamma is defined as this infimum. Maybe we should write it. Okay, so I'm looking at all, so x mu is a standard probability space, and I'm looking at all actions alpha of gamma on standard probability spaces, and G alpha is the corresponding action groupoid. So I look at all action groupoids, I compute the truncated, n-dimensional truncated Euler characteristic, and I take the infimum. Okay. And so now if you think about dimension 1, this is not what Damian calls cost in his seminal paper. It's the cost minus 1. Okay? But Damian agrees with this definition. Okay. This should be called cost. And then notice that on the right side, I don't talk about the cost of standard Borel groupoids. I talk about the truncated Euler characteristic because that's not the right definition of a cost. To get to the cost of a standard Borel groupoid should take into consideration of all actions of the groupoid, just like the group. So you should think of the group as a groupoid, right? Okay, so these two concepts rank gradient and n-dimensional rank gradient and dimensional cost come together in a higher dimensional version of the Abert-Nikolov theorem, which says that let gamma k be a filtration of a group gamma of type Fn, and so think about finitely presented group, then you're thinking about the 2 cost and the 2 rank gradient. And so let alpha be, how much time I have? I don't know if 5 minutes? Okay, then I will move faster here. So I assume that now you have the coset tree, the group acts on the coset spaces. This induces an action on the coset tree, which induces an action on the boundary of the coset tree. And this action is by homeomorphisms and preserves the natural probability measure on the boundary. And then the theorem says that the n-dimensional rank gradient is equal to the n-dimensional truncated Euler characteristic of the action groupoid, which I guess in older terminology we'll call it the cost of the action groupoid. Okay. You don't want to do that. Okay. Now, connection to L2 numbers. Well, his seminal paper on standard Borel equivalence relations, L2 numbers of standard Borel equivalence relations, Damian proves Morse inequalities. Here, R is a standard Borel equivalence relation, right? And then on the left side, we have the truncated Euler characteristic. On the right side, we have the alternating sum of L2 numbers. I will make one fast remark. So the truncated Euler characteristic appears in Damian's paper. He doesn't give it a name, but it's there. So the idea of n-dimensional cost is somehow present there. But Damian works with simplicial complexes, not CW complexes. Okay? In fact, he looks at fields of simplicial actions on fields of simplicial complexes. Well, we decided that simplicial complexes are not the right type of objects to work with. But then, of course, to recover this, either you have to rewrite everything in terms of CW complexes, or you have to prove some sort of CW approximation theorem. The problem is that, you see, CW complexes are more flexible, and so you can have cases where everything is well defined if you work with CW complexes, but if you try to make a simplicial approximation, the space explodes because you need too many simplices. So you get in some dimension infinite measure. So that's another reason why it's better to work with CW complexes. And then in the same paper, Damian raises this question: do we always have an equality? And I don't have time, eh? So I end with no. I will show you a theorem. No, we don't have equality. The Morse inequalities are not always equalities. Here is a result. So you take any positive constant, and you take n greater or equal than 2. Okay, this doesn't hold. I mean, I don't know in dimension 1 what happens. Then there exists a right-angle Artin group A, such that the n-dimensional rank gradient minus alternating sum of L2 numbers is greater or equal than C. Okay. Yeah, and this is true for every normal filtration with trivial intersection. So what this says? Remember this. Now we know that this rank gradient, n-dimensional rank gradient, is the same thing as the truncated Euler characteristic of the action groupoid. But because of this trivial intersection, because the subgroups are normal, this is a standard Borel equivalence relation. Okay, and on the right side, you see they are the L2 numbers of the group, but they are actually also the L2 numbers of this equivalence relation. So this really shows you that the gap here can be arbitrarily large.
For free action.
For
PNP free action.
free actions, yeah. Let me stop here. Very much.
So, do you have questions? And just one remark. So this talk was recorded, so if you have questions, it will be recorded as well. You still have questions?
When you define type Fn for a measure preserving standard Borel groupoid, you're asking that at every cell the measure is finite. Is it possible that if you sum over every dimension the measure is infinite?
Oh, no, because I'm thinking about something finite dimensional.
Ah, okay.
Yeah, because you see, I'm thinking about the n skeleton. So it's of type Fn if in the n skeleton you have a finite measure of cells in each dimension.
I see.
Yeah.
Thanks.
Oh, but what you're right is you're saying something interesting, because then you know it's of type F infinitive and only if it's of type Fn for every n. But then now exists this possibility. So exists this new idea that you might have a finite sum when you sum over all dimensions. So it can be F infinity and not have this property, and it can be F infinity and have this property.
Hi, thanks for the talk. So this could be a dumb question because I know too little about algebraic topology, but in the third row, so if you're given a measured groupoid, let's say even some special ones, let's say equivalence relations or transformation groupoids, is there a way to go back? So is there a way to explicitly construct a classifying space?
Yes, I should. Thank you very much. I didn't say this, but yes, everything has a classifying space. Yeah. You can always go back.
Do you have other questions? Okay, so just before we send the speaker again, I have a few announcements. So if you have questions about funding, I'm the guy you can ask. And if you want to work in some room, so François told us about that this morning, but you can open a few rooms with your key card. So in particular, there is one which is called Café des Calanques, which is just behind the new auditorium, where there are blackboard, etc. It's perfect to work together. So you can use your keycard to open it. And last announcement, the dinner is at 7:30. Okay, and so thanks the speaker again.